Good morning or afternoon, ladies and gents. So this is going to be our second video on vectors. In our previous one where we introduced it, we effectively showed you guys the Cartesian forms the vectors can come in. For today, it'll be re-observing Cartesian forms and then introducing polar forms. And one of the key things about this, being able to convert between one form and the other. So all we need to do is express these vectors in both Cartesian and polar form. Now you guys should know from our previous video, and if you haven't written this down, make sure you include this, that you could show a vector, in this case, U underlined, in three possible forms in Cartesian. Either it'll be in brackets X, Y, which we've already shown for it here. We could do it in matrices form, X, Y, or we could represent it as xi plus yj. This is something you're going to see a little bit more on in year 12 and potentially a bit more through the year, but I digress, something else there. Effectively for a polar form, instead of showing it as our xy components, and I know I can't see it right here, you'll see it in our next part here. Polar form looks at effectively the magnitude and the angle of the vector. Now, if we wanted to represent that magnitude, it's actually going to be using something which we should know, Pythagoras. If you've got three sides of a triangle, A, B, C, and you want to try and find the hypotenuse, C, the easiest way to do it is to use the formula C equals the square root of A squared plus B squared. In this case, to represent the magnitude of a vector, note the two lines to represent the number. The magnitude of the vector is the square root of your x value squared plus your y value squared. So whether you've got it written in coordinate, matrix, or IJ form, you should easily be able to find a magnitude for this. With respect to the angle, get onto that in a little moment. When we represent our polar form, instead of going x, y, how we want to represent it, and it's just over here, the vector is represented by the magnitude, in this case lowercase r, and its respective angle. Try and find this angle. We need to know a little bit of previous stuff, not the Pythagoras I mentioned, but trigonometry. So, to convert between polar and Cartesian, you need to recall the basics of SOHCAHTOA. Now, we're going to go through quite a few examples with this, and the reason is I want you guys to recognize it here. So, for our first set of examples, 1A through the D, convert the following from Cartesian form to polar form. So you're going to see four sets of vectors. And in fact, I'll show you the first. Well, I can show you all four straight up here. It's fantastic. All four of them with their XY, XY, XY components. When we draw it up, and guys, you're going to see this, always draw your vectors because of the positive and negative notation, or the negative positive, or the negative negative. Make sure you recognize which of our quadrants it'll fit in. Positive positive, positive x, positive y. Negative positive, negative x, positive y, and so on and so forth. We're effectively going to convert between our xy into our magnitude and our angle. So, for our first one, our first vector is represented 2, 5, 2, 5. To find the magnitude, we use the formula. The magnitude is the square root of x squared plus y squared. So in this case, the square root of 29, which I'm denoting from its third form into a decimal, 5.385. If you ever get a question for vectors that say leave it in its absolute, you'd have to leave it at square root 29, but it's just saying convert. So in this case, we'll convert to our decimal. For our angle, in this case here, we need to find the unknown angle. Now, for this one, think about it like a triangle, specifically a right angled triangle for trigonometry. We've just determined our hypotenuse. If we have our opposite and adjacent value and we need to find the angle, we need to use our inverse tan ratio. So the angle in this case is equal to the square root of tan, or tan to the -1, opposite over adjacent. Our opposite is 5, our adjacent is 2, so it's inverse tan brackets 5 over 2 close bracket, which gives our angle at 68.199 degrees. Therefore, for our Cartesian form of vector 2, 5, its polar form is 5.385 at 68.199 degrees. You'll see this as we continue through. For our second vector, in matrix form, -3, 1, we've represented it in our quadrant. All we need to do is find our magnitude and our angle. So again, same basic thing. R equals the square root of x squared plus y squared. Substitute values, and then go from surd to decimal form. For our next part, however, this is a bit tricky. Because we are given a triangle in an opposite direction, we aren't given the full angle itself. We're given the angle within the triangle. We know that the collective total of our angle is 180. So when we find our angle, we aren't just putting this as the answer. We need to find our angle and subtract it by the total of 180. Straight line angle is 180 degrees. So to find angle 1, we still use our inverse tan. Inverse tan opposite over adjacent. Substitute values. We get our 18.435 degrees. And then to find our total angle, it is 180 minus 18.435 degrees, which is 161.565 degrees. Therefore, the polar form of V is going to be 3.162 at 161.565 degrees. These next two you're going to see are going to show something a little bit different. You're going to notice in one or two of my examples in the future, it even catches myself out, and I show you guys for it here. And this is something I need you all to observe as well. Remember, if we are looking at angle in the first and second quadrants, it's positive. Remember that from our first video. If it's across quadrants 3 and 4, it's negative. So remember this one. So, for example, 1c, we're given our vector in the Cartesian form 4i minus 6j. So we draw it up. Positive x value, 4, negative y value, 6. We find our magnitude and angle. We use the same issues we've done with our magnitude in the past. Square root of x squared plus y squared gives us our value of 7.211. We still find our angle, which in this case, inverse tan, substitute values, 309 degrees. But because it's found within our fourth quadrant, we make it negative. So our final answer for this one, the polar form of our angle V, of our vector V, it has a magnitude of 7.211 at negative 56.309 degrees. Final one for this example. We've got a vector which has got a negative x and a negative y value. So this one has to be in our third quadrant. We do the same thing we do to find our magnitude, substitute our values, which ironically is the exact same as our top one. To find our angle for our triangle here, we still use inverse tan, but because we're trying to figure it out here, we still minus it from 180. And because of its location, we then denote a negative angle point. So inverse tan 2 over 5 is 21.861, or 801, sorry, my apologies. Then we go 180 minus our angle, which in this case is 158.199. And again, because of its respective location, we denote the negative to it. So the polar form of our vector is 5.385 magnitude at negative 158.199 degrees. I know I've made a few of the errors for it. Always include our degrees symbol to make sure you're getting full marks here. So that's obviously our first part for the example, converting from one side to the other. I'm sure we can all pick it here. For the next section, we are simply converting back from polar form to Cartesian form. So for each of our examples, let's go for this one here. Our polar form vector is to magnitude of 2 at positive 40 degrees. So we draw it up. We've got our hypotenuse at 2, with an angle at 40, and we need to find our x adjacent and y opposite values. In this case, to try and find our first value here, so x, because we're looking at the adjacent, we need to use our cos. Cos angle is adjacent over hypotenuse. We substitute our values in, we rearrange it so we isolate our x, or our unknown value, and we get our answer, which in this case is 1.532. Because we're trying to find our opposite, or our y value, we use sine. Sine of angle equals opposite over hypotenuse, substitute values, isolate y so everything else is on the other side, plug it into a calculator, 1.286. Therefore, our vector in Cartesian form is 1.532 at 1.286. There's nothing in this question about keeping things absolute, so we can put them down to our decimals. Continuing on through. So, for our next example, we've got a vector which has a magnitude of 8 at 150 degrees positive. So we represent it here. We don't need to use anything to figure out our missing angle within the triangle. If we know the total of a straight line is 180 degrees, it is just going to be 180, take our known angle, 150, which gives us 30. This allows us to now use our trigonometric ratios, I always get that word mucked up, to determine our x and y values. So for x, our angle's close by, we need to use our cos ratio. We plug it in, we substitute known values, we rearrange so x is on its own, and we get our answer. The thing is, because our vector is in our second quadrant, we know that x value must be negative. I can't stress this enough, ladies and gents. Draw your vectors. You start forgetting to draw them, you will start forgetting to put these notations, and therefore you could lose marks. To try and find y, we know we're going to be using our sine ratio. We substitute our values, and because it's in the second quadrant, we leave our y value positive because y is positive. And then we just pop it in. The Cartesian form of vector v is negative 6.928 at 4. Third example, we've got our polar form vector magnitude of 4 at negative 20 degrees. So we draw it up over here. We've got our angle at 20 degrees. We've got our hypotenuse at 4. We can find x, y. Exact same principles. Substitute values, but because we're looking in our fourth quadrant, our y value must be negative. So once we work out x, we work out y, add the negative notation to it, substitute it into our answer. And then for the grand finale, 3.2 magnitude. Oh, I haven't written the v equals there, but I'm sure we can read in between the lines. At 220 degrees, we draw our vector all the way across. We need to get it appearing as a triangle. Remember, just like a little triangle here. So if our total is 220 degrees, and we know our straight line is 180, we just go 220 minus 180 to get our angle inside the triangle, 40 degrees. We can then use our respective cos and sine ratios to find x and y. Because of the location of our vector, we know that x and y values must be negative, negative x, negative y. So once we find our answers, denote them as negatives, and then show that for our answer, a vector v in Cartesian form is negative 2.451 at negative 2.057. And that's all it is. So give these questions a crack, guys. You're going to observe it's more repetition more than anything else. And then we'll get on to our next one. Thank you very much.